Okay, in this video, I'm going to discuss the multiplication rule of probability. And this is the rule that allows us to determine the likelihood or the probability of two or more things happening in sequence or one after another. Now, we've already talked about the addition rule for probability. It is the rule we use to determine the probability of multiple events happening at once or out of a single trial of an experiment. So now we'll discuss the problem of calculating the likelihood of a sequence of events. And before we do that, let's look at one definition that we'll need, and that is the definition of independence. So two events are independent if the occurrence of one does not affect the probability of the occurrence of the other one. So what that means is, let's picture four chairs. 1, 2, 3, and 4. Okay, so that's 4 chairs. And let's say there's 2 people, you and someone else. Now, let's say you're assigned seats at random. Let's say this is chair number 1, chair number 2, chair number 3, and chair number 4. And you have let's say 4 numbers on pieces of paper and a hat. You pick a number at random. Whatever number you pull, that's the seat that you sit in. Okay, you are going to pick second. So someone else is going to pick a number, sit down. Now you are going to then pick one of the 3 remaining numbers and take that seat. What is the probability you end up sitting next to this person? Well, let's look at what could possibly happen. So let's switch here to red. All right, let's say that person number 1, chose number 1. So they're sitting in seat 1. So now, what is the likelihood that you pick a number such that you'll be sitting next to this person? Well, that could only happen if you're in seat number 2. So the probability that you're sitting next to this person would be 1 in 3. You have 3 numbers left, the 2, the 3, and the 4. And since of those 3 seats, the only one that's next to person number 1 is seat number 2. So it's a 1 in 3 chance. All right, but what if person number 1 is in seat number 2? Well, now the 3 remaining seats, number 1, 3, and 4, you're going to pick one of those numbers at random, and now 2 of them are next to person number 1. So now you have a 2 in 3 chance of sitting next to this person. So your probability changes depending on what happened first. If person number 1 was in seat number 1, your probability of sitting next to this person was 1 out of 3. But that probability changed if person number 1 was seated in seat number 2. Well, now there are 2 seats next to this person. So the likelihood you pick a seat next to this person is now 2 out of 3. So these 2 events, the first person picking their seat and you then picking your seat, those 2 events are dependent because depending on where the first person sits, well, that changes the probability of you sitting next to that person. Okay, so in that case, those events are dependent. If the occurrence of one does not affect the probability of the occurrence of the other, then we say those events are independent. And just like our definition of mutually exclusive or disjoint affected how we apply the rule of addition, the addition rule of probability, well, whether or not events are independent or dependent directly affects how we apply the rule that we're talking about now, the multiplication rule. All right, so another example, let's say you pull 2 cards in succession, so one after another, from a standard deck of 52 cards. So you have 52 cards, you pull one, then you pull a second one. Now the question is, what do you do with the first card? You pick a card, any card, and then what? Do you replace the first card before drawing again? In that case, you're back to the original 52 cards. So regardless of what happened first, with that first card, it doesn't affect the likelihood of pulling any card on the second pull. Or do you not replace the first card? In that case, when you draw card number 2, now you're down to 51 cards. So the probability of any card being drawn changes from 1 in 52 down to 1 in 51. So this is really important. When we're dealing with the sequence of events, it's really important to determine, does what happens in step 1, does that affect what happens in step 2? Okay, so we'll refer to these things as with replacement. Let's say with replacement. These are really common statistical terms. With replacement and without replacement. With replacement is an independent process, and without replacement is a dependent process. Okay. Now, it turns out that independent events are much easier to work with. So, we have this 5% guideline. And what the 5% guideline says is that even if your events are dependent, and we'll see later that dependent events require a little bit more, or are a little bit more involved in terms of calculating the probabilities. Even if the events are dependent, if the sample size that you're choosing is less than 5% of the size of the population, then we could treat dependent events as being independent. Now this is not something you have to do. This is like let's say this is an option to simplify calculations if precision isn't the highest priority. Okay, so now let's revisit. We talked about the game of craps briefly in the last video. Again, you don't have to know anything about the game itself. All you have to know, and this is what the table looks like, all you have to know is that a winning roll is a 7 or an 11 at the beginning of the game. Then things change, but all we care about right now is basically it's just roll 2 dice, you win with a 7 or an 11. Now, when we talked about what is the probability of winning in the last video, which is basically what is the probability of rolling a 7 or an 11, and we got that the probability of winning once, the probability of a single win, was 2 out of 9, or about 22%, a little more than 22%. So now that we know the probability of winning once, what is the probability of winning 5 times in a row? Winning on your first 5 consecutive rolls. All right, so let's think about this. On your first roll, one of 2 things could happen. You either win or you don't win. Okay, so, and that's here, this first split. On the first roll, you have a 2 in 9 chance of winning, which means you have a 7 in 9 chance of not winning. Okay, so let's say you win on the first roll, because we're looking at you have to win 5 times in a row. That's what we're concerned with now. Let's say you win on your first roll, then you roll again. Rolls of the dice are independent because you're dealing with the same 2 dice, nothing changes. So if you win the first time, then you again have a 2 in 9 chance of winning and a 7 in 9 chance of losing. So forget about the probability of winning 5 times. What's the probability of winning twice? Well, it basically comes down to 2/9 of 2/9. And the word of tells us to multiply. So the probability of winning on your first roll and then winning again on your second roll is 2/9 of 2/9, or win and then win. 2 times 2 is 4. 9 times 9 is 81. So the probability of winning twice in a row is 4 out of 81. And we could look at the other the other 3 scenarios. If you win and then you lose, you're here. If you win and then you don't win, and so on. But we're just concerned with the 5 wins in a row. Now, extend this from 2 rolls to 5 rolls. Every consecutive roll, any additional roll, you always have another 2/9 probability of winning. So 2/9 of the previous probability. So if we wanted to look at 3 rolls, 3 consecutive wins, it would be 2/9 of 2/9 of 2/9. And this brings us to the multiplication rule. Before we calculate the final probability, this brings us to the multiplication rule. When finding the probability that event A occurs first and event B occurs next. We obtain this by multiplying the probability of event A, just like we did in the tree diagram. The probability of event A by the probability of the event B, because we're taking a part of a part, basically. And the last example was 2/9 of 2/9. But, and this we'll talk about in more detail later on in this slideshow, make sure that the probability of event B takes into account what already happened in event A. And this goes back to the example I was talking about with pulling 2 cards from a deck, one after another, whether or not you replace the first card. All right, so notation-wise, P of A and B. Now remember, I mentioned this in the last video. This word "and," the implication there is "and then." Not A and B at the same time, but A happening first and then B happening second. So when I said takes into account the previous occurrence of event A. So event A happens first. So the probability of A and then B happening is the probability of A happening first times the probability of B happening, assuming A has already happened. Now this second one with the B and the vertical line A. So this is called the conditional probability of B. It's the probability of B under the assumption that A has already happened. So this is like the probability of A and this is the probability of B, but since B happened second, the probability of B might have something to do with what happened first. Now, if events A and B are independent, well then A happening has no effect on B, whether or not B happens. So if A and B are independent, then the probability of B given A is just the probability of B. A has no effect on this. All right, so, and that's again down here, the probability of A and B. For independent events, this A doesn't matter, doesn't affect the B, so it's just probability of A times the probability of B, and that's what we see down here. Now, you may see in the textbook a formula that isolates the probability of B given A. All that means is we divide both sides by probability of A and bring this to the other side. So it's not really its own separate formula. It's just moving the probability of A from one side to the other. This is not very important. Okay, so let's actually see if we have. Yeah, let's go to this. Let's finish up this example, and then we'll come back. So going to finish up the craps example, we looked at the winning on the first 2 rolls, but if we extend that to 5 consecutive rolls, it would actually be to win 5 times in a row. The likelihood would be 2/9 of 2/9 of 2/9 of 2/9 of 2/9. And if you were to pop that into a calculator, you would get about 0.0005 or 0.05%, which is about a 1 in 2,000 chance of this happening. Moral of the story, if you win 2 or 3 times, stop, take your money, leave. The probability of consecutive wins becomes very, very low. Okay. So let's go back to the example of drawing 2 consecutive cards, and let's say specifically, what is the probability of drawing 2 face cards, one after another? And the key, and this is very important in the problem, without replacing the first. So you draw the first card, you leave it out of the deck, and from the remaining 51, you select the second card. So the probability of a face card and then a face card again. Okay, so that's the probability of A times the probability of B, given that A has already happened. So let's look at card number 1. There are 12 face cards in the deck. 4 jacks, 4 queens, and 4 kings. So for the probability of A, there are 12 cards in the deck out of 12 face cards in the deck out of 52. So that's the probability. The first card is a face card. Now, all this conditional probability stuff, I mean, don't make this more complicated than it needs to be. All this conditional probability stuff is saying is that at each step in the sequence, you have to update your numbers based on what has already happened. So if you pull 1 face card out of the deck, that means 1 face card is gone. That means there's 11 left. And if there's 1 card missing, that means there's only 51 choices left. So the probability of B happening is now 11 out of 52. And this is conditional probability. All it means is, no, not 52, 51. And this is conditional probability. All it means is you update your numbers at each step in the sequence of events based on what's happened previously. All right, so 12 over 52 times 11 over 51. You can pop that into the calculator. We get about 0.05 or 5%. So you have about a 5% chance of pulling 2 consecutive face cards. And that's it. That's the multiplication rule with conditional probabilities. So one more example. There's approximately 7.4 billion people on the planet. It's probably closer to 8 now since I've written up these notes. But let's say there's about 7.4 billion people on the planet. Let's say every single person, man, woman, child, infant, everyone, takes a 20-question test. 20-question multiple choice test. Multiple choice, very simple. You have 4 options, A, B, C, or D. One answer is correct, the other 3 are wrong. And let's say everyone guesses. You just fill in 20 bubbles on a little Scantron. So 7.4 billion people guess on each of these questions on a 20-question multiple choice test. How many 100%? How many perfect scores would you expect? Well, let's think about this in terms of the multiplication rule. It's not very difficult because the multiplication rule allows us to look at each individual step separately. So the probability that so let's look at just one question. The probability that one single question is correct is 1 out of 4. There's one correct answer out of 4, and if you're guessing, you have a 1 in 4 chance of guessing correctly. Now, the multiplication rule says this is a sequence of 20 independent events. You guess on question 1, and then you guess on question 2, and then you guess on question 3, and so on. So, to guess all 20 questions right, one after another, well, the multiplication rule says, let's do a little writing before we pull up that slide. The multiplication rule is saying, well, at step 1, you have a 1 in 4 chance. At step 2, you have a 1 in 4 chance. Step 3, another 1 in 4 chance. And this keeps going until step 20, where you answer the 20th question. You guess on the 20th question. So it looks like the probability of guessing right, of getting 100% on a 20-question test, when you figure billions of people in the world, someone's going to get it right. It's like winning the lottery. In this case, 1 over 4 times itself 20 times, or 1 over 4 to the 20th power. So that's this, 1 over 4 to the 20th power. That's actually 1 over a really big number. And this is about 1.1 trillion. So, according to the multiplication rule of probability, you would expect that if 1 trillion people took this test, one of them would get it right. So, in actuality, and let's say there's 8 billion people in the world, even if everyone took this test 10 times, you would expect no one to get 100%. You are more likely that every single person gets this test at least one question wrong. And this is the multiplication rule applied to independent events. All right, so that about does it for, that's the last one. That about does it for this set of notes. Next, we'll move on to counting techniques.